The first type of problem that you're going to see is our simplifying problems from lesson 14.3. In that lesson, we learned that when we simplify, we're trying to break it down to make it as small as it can possibly be, try to clean up any of the messy part to it. If we can get it down to one trig function, that's kind of our best goal, but it's not always possible. You do not need to have any of the trig identities memorized. They will all be given to you on one sheet. So our two main strategies that we go for are making substitutions from the trig identities or changing into sines and cosines. So pi halves minus x is one group of those trig identities, but we only have identities for sine, cosine, and tangent, the main three. So for number one, the first thing I'm going to do is turn this thing into 1 over sine. Cosecant is the reciprocal of sine, so I can turn cosecant into 1 over sine. Then there is an identity for sine of pi halves minus x, or x minus pi halves, and that is the same thing as cosine. So then as our final answer, what's the same thing as 1 over cosine? We'll flip it back over, and that's secant. Secant is the reciprocal of cosine. Okay, 22, or number 2, has these fractions in there. Instead of having them as the fractions, I'm going to go ahead and flip them back to just making it a regular thing. So instead of 1 over sine, we can change that to cosecant, and there's a squared outside, which means this is cosecant squared. And the reciprocal of tangent is cotangent, and it's squared, so I can make that cotangent squared. And then one of our identities under the Pythagorean ones, where we have a lot of squared things in ones, says that cosecant squared is exactly the same thing as 1 plus cotangent squared. Okay, that's one of our identities, that cosecant squared x is equal to 1 plus cotangent squared x. So I can just swap that out. And that's helpful because then I end up with 1 plus cotangent squared minus cotangent squared, and plus a minus are going to cancel each other out, and this whole thing just turns into 1.
Is it possible to zoom?
Not really.
Okay.
Just the writing, like my handwriting's too small, or the problems themselves.
Just the handwriting. Is that 1 plus cotangent?
1 plus cotangent squared x. Yep. For the third one, we have a group of identities that are called our negative angle identities. And they talk about what to do when we have a negative x in there. The one for tangent says that tangent of negative x is equal to a negative tangent x. But in this problem, we have something else kind of going on here because it's squared. And what happens when you square anything? It becomes a positive, right? Because you're multiplying it by itself. So if it's a positive and you multiply it by itself, it's positive. If it's negative and you multiply it by itself, it's going to be positive. So no matter what, because this is squared, we can just get rid of that negative, because that's one thing that squaring does, is makes everything positive. And then I'm going to write these things as sines and cosines. That's one of our two main strategies. One is the substitutions, the other one's turning things into sines and cosines. Tangent is sine divided by cosine. So I'm going to write that as sine squared over cosine squared. In the bottom, I'm going to write that sine squared as sine squared over 1. What's the same thing as dividing by a fraction?
Multiplied by the reciprocal.
Multiplying by the reciprocal. So I'm going to leave that top one alone. But I'm going to flip over that bottom one and multiply by it. Instead of dividing by sine over 1, I'm going to multiply by 1 over sine. Which cancels out the sines and leaves me with 1 over cosine squared. And 1 over cosine squared is the same thing as what? Secant squared. Okay, two main strategies. Look for substitutions from the identities, which you don't have to have memorized, and change into sines and cosines. You do have to have that memorized, how we can move back and forth between the trig functions, changing them with cosecant and sine, secant and cosine, or tangent being sine over cosine. For the second group of identities, we use the same strategies, but we have an equation, and we're trying to show that the two sides of the equation are the same. So I'm going to use my strategy of change things into sines and cosines. So cosine over 1, secant is 1 over cosine. Sine over 1, cosecant is 1 over sine. I don't know why that little thing is on the screen, or how to make it go away.
Is that 1 over sine of y?
Yeah. So the cosines are going to cancel and leave 1. The sines are going to cancel and leave 1. And 1 minus 1 is indeed 0. The goal of verifying is to make this thing something that is obviously true. So at the beginning, it's not so obviously true. At the end, 1 minus 1 is definitely 0. That's obviously true. For the next one, because it's an equation, I can do whatever I want, add, subtract, multiply, divide, as long as I do it to both sides. So I'm going to begin by subtracting 2 from both sides to get all those constants together. And when I see a lot of squared things in ones, I start to think about those Pythagorean identities. So when I look at those Pythagorean identities, I see one that actually exactly matches what this is. That means this thing's done. If it matches an identity, identities are true, and so this must be true. Okay, so you can either get it down to something where the two sides are exactly the same or abundantly obvious that it's true. 1 minus 1 is 0 is definitely true. Or you can get it to match an identity because our identities are known to be true. And that one exactly matches an identity. Right, so that was the stuff that we learned in section 14.3. 14.4, we went on to learn about solving equations. So on this one in the directions, it has this phrase, the interval 0 to 2 pi. What that means is we did two different types of solving equations problems. With one of them, we put a plus 2 pi n at the end of it, which means you can keep on going around in circles forever if you want. On the interval of 0 plus 2 pi, that means we don't want to keep going around in circles. So we're not going to put a plus 2 pi n on our answer. Okay? We just want our first set of answers that happens in the initial circle. To solve, our first step was treat it like an equation and get the trig part alone. So I'm going to begin by subtracting 4 secant of theta from both sides. So I get all those together. And then I'm going to divide by -3, which gives me -2 is my secant of theta. That's our first step. get the trig part alone. Okay, and remember these problems are usually worth several points. So even if you can't complete a problem, you know, like, I know I'm not gonna know how to finish this problem out, at least do as much as you can do. Because at this point you've earned 1 point, right? And that's better than nothing. So first step, get the trig part alone. Second step, figure out which angle this thing is talking about. So I can write anything as a fraction by dividing by 1. Secant doesn't have a SOHCAHTOA, but it's the reciprocal of what? Cosine. And cosine is adjacent over hypotenuse, so this is then hypotenuse over adjacent. The triangle that has a hypotenuse of 2 is our 30, 60, 90. And the angle that is adjacent to the 1 is the 60. So we're going to be working with 60, but in radians that's pi over 3 because pi is 180 and 180 divided by 3 gives us 60. Our last step is selecting our quadrants and finding the angles in those quadrants. So this problem uses secant. None of those letters stand for secant. Those stand for our main ones, sine, cosine, and tangent. So when we're thinking about secant, we really want to be thinking about cosine because that's its partner. Our equation says that cosine is a negative value. So I want to choose the places where cosine is negative. All means all of them are positive, and I don't want that to happen. And C means cosine is positive, and I don't want that to happen because I want cosine to be negative. So I'm going to choose my answers in the S quadrant and T quadrant. To find those answers, I'm going to cut each half of the circle into 3 pieces since we're working with pi thirds. And I'm going to count how many pieces I have to go to get into those 2 quadrants that I want. So in the S quadrant, I have to go 2 pieces. And in the T quadrant, I have to go 4 pieces.
Can you explain why we need the SOT quadrant?
We're working with secant, but secant isn't one of our main functions. So we want to think about its partner main function, which is cosine. Then our equation says that it's equal to negative 2, so we're working with negatives. So we want the places where cosine is negative. All means all are positive, and we don't want a positive. C means cosine is positive, and we don't want cosine to be positive. Here's our equation says that cosine's negative. So then we're going to select the opposite 2 quadrants.
So if we were trying to find tangent, and tangent was supposed to be positive, it wouldn't be in the positive.
If tangent is supposed to be positive, then it would be in the T quadrant. Yeah. If it's a positive in your equation, you want to choose that trig function and choose the all. If it's a negative in the equation, you want to choose the opposites. I'm going to skip number 7 just for time and to give you one to try. There's 2 more equations on the top of the back, so we'll solve those out. So these directions say find the general solution. This means at the end of it, we're going to tack on a plus 2 pi n. That just means you can go around in circles. So for number 8, our first step is get the trig functions together and then get them alone. So I'm going to subtract a cosine from both sides. I get 2 cosine of x is 1. And divide by 2. And I get cosine of x is 1/2. So that's your first step, get the trig function alone. Second step, figure out what angle this is talking about. So cosine is adjacent over hypotenuse. The hypotenuse of 2 and next to the 1, that's our 60. which is pi over 3. Then for choosing our quadrants, this time our equation says cosine and it's equal to a positive 1/2. So I want the quadrants where cosine is positive, which are the all quadrant means all are positive, and the C quadrant means cosine is positive. This is the opposite of the last problem, because in the last problem we had cosine being negative. So then I'm going to cut each half into 3 pieces. In the all quadrant, I just go one of those pieces, so that's 1 pi over 3. And then we're going to do a plus 2 pi in on that, which means you can just keep rotating around in circles forever, as long as you end at that same spot. And then in the C quadrant, I have to go around 5 pieces. I get 5 pi over 3 plus the 2 pi n. For number 9, I'm going to start by adding the 1/4 to both sides. Our goal is to get the trig function alone, and it's not totally alone right now because it's sine squared, it's not just sine. So to undo a square, we need to take a square root. When we take a square root of a fraction, we take the square root of the top and the square root of the bottom, and we get a plus or minus. Because 1/2 times 1/2 is a 4. But negative 1/2 times negative 1/2 is also 1/4. So when you take a square root equation, you get a plus or minus. I have a sine of 1/2. Sine is opposite over hypotenuse. Get a hypotenuse of 2, and this time I want to be opposite of the 1, which points to the 30. Or pi over 6. 180 divided by 6 is 30. For our quadrants, on this one, I want sine to be positive or negative, which means it could go in any of the 4. Sine is positive, and all in sine, it's negative in tangent and cosine, and we're okay with either of those things happening because we got that plus or minus in the equation. So then we cut each half into 6 pieces. And we always want to go to the piece that is closest to the x-axis. So in the first quadrant, I just go 1 piece. So 1 pi over 6. In the second quadrant, I go 5 pieces. In the third quadrant, I go 7 pieces. In the last quadrant, I go 11 pieces. We always want to go to the one that's closest to the x-axis, so either just before it or just after it. And then all of those, I'm just going to throw a plus 2 pi in onto the end of the whole thing. All right. For the next group, it doesn't tell you which identities to use, so that means sometimes you have a choice. You could use your double and half that we learned yesterday, or you could use your sum and difference. Most people prefer sum and difference, at least for sine and cosine, because yesterday as we learned with the double and half, it had for sine and cosine that huge square root, and then we had to decide positives or negatives. So I like personally to avoid those when I can, but some people don't mind them.
Please excuse this interruption. Any student involved in chapel worship this morning, please go to the cafeteria.
So I'm going to do sine of 45 minus 30 to get 15 and use my sum and difference formulas here. So then I plug into that formula, which says sine u cosine v minus cosine u
We're gonna have that on the test.
sine v. Yep, you'll have all the formulas. Then I want to evaluate these things from my special triangles. So from my 45, 45, 90, or from my 30, 60, 90. So in the 45, 45, 90, sine opposite over hypotenuse is 1 over square root of 2. Cosine of 30 adjacent over hypotenuse is square root of 3 over 2. Cosine of 45 is 1 over square root of 2. And sine of 30 opposite over hypotenuse is 1 over 2.
For the 30, 60, 90 is opposite, always opposite of the 60.
No, it depends which angle you're working with. So since I'm working with a 30, I want to focus on the 30, and then opposite is 1, and adjacent is square root of 3. And the 1 is always opposite of the 30, and the square root of 3 is always opposite of the 60. Those don't move. Then we're going to multiply the two groups together. You should always have a common denominator at this point, so then you can just put the tops together over the same bottom. We're going to go ahead and look at number 13. 13 is given in radians. My first step in radians is to turn it into degrees. So I'd multiply by 180 over pi, and that gives me 22.5. Which means we have to use a half angle formula on this, because I can't add or subtract to make 22.5. So I'm going to say that this thing is the tangent of 45 divided by 2. Then I'm going to use my half angle formula for tangent, and those will also be provided for you. And it says 1 minus the cosine of u over the sine of u. The cosine of 45 is 1 over square root of 2. And the sine is also 1 over square root of 2. But we can't cancel those. Okay? A lot of students want to cancel those because there's the same thing on both the top and the bottom. But since it's adding, that doesn't work. Okay? So we can't cancel those. But we learned the way that we can clean them up is by multiplying top by square root of 2 and bottom by square root of 2. And then distributing through. So that's going to leave me with a square root of 2 minus 1 over just 1. Okay, so for the last group of problems, we're going to draw the two triangles indicated by the directions. So the first one says that our u angle is between 0 and pi halves, which is between 0 and 90. And that cosine adjacent over hypotenuse is 3/5. The opposite side of that would then be 4. Then for our V triangle says it's between pi halves and pi, or 90 and 180. and that its sine opposite over hypotenuse is 12 and 13. You can find the missing side with the Pythagorean theorem, or you might recognize that it's just a 5. It's going to be a negative 5 though because it's a left. Okay? So draw the triangles out. Okay? Even though they both turned out to be nice numbers, actually draw them out because then I can see if you made a mistake on one of your triangles, like if you forgot that it was supposed to be a negative 5 and you just had a 5, that's going to make all your answers be wrong throughout all of these problems, but I'll only deduct once for having done an incorrect triangle instead of for having done really all 4 problems wrong. So make sure you show me the triangles that you're working with. And then we want to apply the formulas. So for the first one, sine of u plus v. Oh goodness. The formula is sine u cosine v plus cosine u sine v. And then I'm going to grab these from my triangles. So in the u triangle, the sine is 4/5. In the v triangle, my cosine is negative 5/13. In the u triangle, my cosine is 3/5. And in the v triangle, my sine is 12/13. Multiply the pairs, gives negative 20 over 65 and 36 over 65. You should always have a common denominator at this point, so don't reduce them even if you can, because then we can just add them together. Reduce a final answer if you can, but this one doesn't reduce. I'm going to skip number 15 because it's really exactly the same. It's just using a different formula, and I kind of ran into my space there. So number 16, the formula for that is 2 sine u cosine u. This problem, number 16, only has a u in it, so that means we're only going to be using the u triangle. We're not going to refer to the v triangle at all. So in the u triangle, sine is 4/5 and cosine is 3/5. I can make that 2 like a 2 over 1, and then I can multiply all the tops together, 24, and the bottoms together, 25. For the tangent of v over 2, I'm going to look at my tangent half angle formula. There's 2 of them. It doesn't matter which one you use, but I said that I usually prefer to use this one. Now a caution. This problem has a v in it, so we want to use the letter v in our problem. The formula sheet has a u in it, okay? So be careful of that. You want to use a letter that's in your problem. So I have a v in the problem. I want to use the letter v, okay? So I'm going to look at the v triangle for this one. Cosine is negative 5 over 13. Sine is 12 over 13. And then we can simplify that by multiplying everything by the little denominators. That gives me 13 minus 5 over 12. Yes, thank you. I lost my negative. Double negative plus. So that gives me 18 over 12, and that can be reduced down to 3 over 2.